Well, the aerosols means they must be in the air. And we saw an animation which showed that they were flowing all over the place, right? If they're in the air, if air is moving, humidity is moving, then you expect aerosols to move as well, right? So they are getting spread around. Only interesting thing that there are even bacteria that are being carried from Africa all the way to Caribbean and so on. Many diseases like meningitis can spread by, they are also aerosols. Aerosols doesn't mean they are dead, they could be alive. Anything that's airborne and particulates like small, cloud is not an aerosol, right? Dust is. So I think we stopped here. So we consternated a little bit on whether this is a trend or a shift and whether there is a trend here. And we also pointed out that the two trend lines will correlate anyways, but finding the causal relation is always the challenge in science. So statistics is like a fishing expedition. So you look for things. If they don't work, then you have to explain why they don't work, or you have to explain why that is a causal relation. The next big thing is to understand, before you do anything about climate change, you probably want to understand what El Nino may be doing, because El Nino itself may also change, and we'll see that maybe El Nino is doing something different. And we said El Nino is basically the shift of this West Pacific warm pool and the convection to the east. So you create droughts and dust storms and so on here. You create suppressed upwelling, mudslides, floods on this side. But this is what typically we show. We will see that actually this is not always the case, in the sense that the water doesn't need to come all the way, the upwelling doesn't need to get suppressed here, and so on and so forth. And in the context of global warming, we said it matters whether this region will warm more than here and so on. The other question is, depending on how it is warming, what would happen to the El Nino? So we'll see some of that. But in the context of the monsoon, you can look at the long-term anomalies. So again, we are using a climatology that is for the whole 1870 to 2015 or so period. And we already learned that the climatology doesn't have to be the long-term mean. You can make a running mean climatology, which will change the answer a little bit, and so on and so forth. So the blue lines and the green lines above and below are showing excess or dry years, but the drought years here are shown in red and flood years are shown in blue. And the green lines are normal years, which means you are within plus minus 10%. So you can see that the 10% line has been drawn to reduce stress on you. And then El Ninos and La Ninas are noted with these stars in blue and red. What is the point? The main point is that there are many years where there are floods, but they are not El Nino years. So these are flood years, but they are El Nino years. In between, there is a year that's a flood year, but that's not an El Nino year. This is a strong flood, but not El Nino years. And similarly, you have lots of droughts, and not all droughts are El Nino years. Obviously, as we said, about 50% of the droughts are explained by El Ninos, the rest are not. We don't talk much about La Nina, because when there is good rain, we don't worry about it. But obviously, if there is too much good rain, then you have floods, then you have to worry about it. And there is also other details which we didn't get into. There are very few back-to-back drought years, but you can have many back-to-back wet years, because El Nino can persist for multiple years, whereas La Nina can persist for many years, but El Nino doesn't. It just comes, spends all the warm water, and then it disappears. It has to rebuild again, whereas La Nina is cold water building, so it can keep on recharging for multiple years, right? The other thing you have to remember, of course, is that La Nina looks somewhat like a normal condition. You have cold waters in the west, right? If you think about La Nina, it's cold here and warm here, but normal air is also got cold here and warm here. So La Nina is exaggerated normal state. So what are the various mechanisms of drought. Typically, when we do this, we look for what are called atmospheric bridges, which means whenever we perturb a heat source, we said there is waves being generated, mean winds are altered, but there are also waves. So waves obviously propagate typically much faster than the winds or ocean currents. And you also have what are called oceanic tunnels, which means if you make a change here, you expect that signal to go into the Indian Ocean through the Indonesian through flow, and so on and so forth. So there is an oceanic tunnel between the Pacific Ocean and the Indian Ocean, but the atmospheric bridge is, of course, global. What this is showing is what Walker had figured out early on. He looked at the pressure over Tahiti and over Darwin, and he said there is an oscillation here, which he called Southern Oscillation, and that's what he related to the droughts over famines over India. So in this context, you have to then say, why doesn't the Southern Oscillation always create a drought here? One simple way of thinking of that is to take Darwin pressure and correlate it with sea level pressure around, and you can see that the correlation obviously drops as you go farther away. That's kind of the decorrelation scale. And you can see that significant correlations only cover part of India. Okay, this gives you a sense that maybe not all of India is affected by the Southern Oscillation, which would also translate to El Nino, because El Nino and Southern Oscillation are very closely related. Although this doesn't say anything about the mean changes versus the so-called active break or intra-seasonal changes, right? So that is much more of a difficult problem, but there is lots of papers which show that the intra-seasonal variability doesn't change significantly. So you have, so we are saying slightly different things now. When we looked at this particular figure, we said dry years may have longer break periods, whereas normal or wet years may have shorter and fewer break periods. But when we say El Nino is not going to affect the intraseasonal variability much, it is in the long-term sense. You have to look at the long-term correlation, and the correlation is not very robust. These are just 3 years, okay? So if you take all the years, then the story is not that straightforward. In other words, that means we don't know whether there are processes that control the mean rainfall, and then there are processes that control the intraseasonal rainfall. That gets complicated, but people argue about whether mean rainfall is made up of the intraseasonal rainfall or whether that's independent. And there are statistical analyses that show that there is a persisting mode, that's a seasonally fixed pattern of rain, and then there is propagating mode. So there is a combination of things that create the monsoon rainfall. As I said, there is the marine ITCZ that sits there, and then the monsoon trough that sits over there at the foothills of the Himalayas, and you have mesoscale eddies that are going from the marine ITCZ to the continental convergence zone. So you obviously have some kind of a established rain pattern here, and then there is communication between them that adds some masala to the whole story. So obviously that's, when you say a multi-scale system, that's what you get. You get all kinds of time scales that are not neatly separable, even mathematically, because we don't know how it works yet. So going back to the Walker cell, we talked about Hadley cell more than the Walker cell, but as we said, when convergence happens and you hit the tropopause, air not only goes poleward in the Hadley cell, but you also have these zonal cells. So rising air is hitting the tropopause, is going east and west. So you have convergence at the surface, divergence aloft. So that gives you rain over here, and this air is sinking here, where you have high pressure, cold waters, nice weather, no rain, right? So all these regions are dry, and the upwelling and the cold temperatures just reinforce the dry weather. The Walker cell is typically talked about as the Pacific Walker cell, which dominates obviously the global story because this occupies about more than 25% of the planet. And over the Indian Ocean, you have a sinking over here. Remember, this is on the equator, not on land. And there is West African monsoon that we talked about, which has convergence and rain. And you have the Amazon convergence and rain. So these three bits make up the Walker cell, which is the zonal cell, whereas the Hadley cell is the meridional cell. So you can imagine immediately that El Nino is going to make a perturbation to this Walker cell. Then you have to connect it to the local Hadley cell that we talked about. So monsoon active break periods are basically having sinking here, rising there, or sinking here and rising there. So you have this local Hadley cell that's doing a back and forth. So if you look at El Nino conditions, you have warmer than normal sea surface temperatures here. You have colder than normal. There's a mosquito running around. Colder than normal SSTs here, and then it gets a little bit less organized and less robust in the Indian Ocean. And you can see that the rising or convergence has shifted to the east, and that means you also have shifted the other parts of the Walker cell. So you have sinking over colder waters, higher pressure, so Darwin has higher pressures and so on. So if you perturb the Indian part of the Walker cell, then you also have to think that maybe that also affects the Hadley cell, which would be your intraseasonal oscillation. So what I'm saying is that we are always focused on the land-sea thermal contrast and the southwesterly winds and so on, but there is a global context to the monsoon, how things shift. There are also relations to how much snow there is, because that determines how much land warming you get. It's also related to warming or cooling over the North Atlantic and North Pacific and so on and so forth, which just confirms that the Hadley cell and the Walker cell are constantly talking to each other.
So does the Walker cell have anything to do with why the ITCZ gets cut into two, split into two?
Here? Oh, you mean no, that is, Walker cell is the zonal cell, which is largely driven by the large massive convection here and over here. So this convection is year-long and persistent.
Then what splits it into two just there?
Yeah, so as we said, the ocean remains so warm throughout the year that you can drive dynamic ascent. It always comes down to dynamic ascent, which means you need warm waters and rising air, and that is replaced by convergence. That is what drives dynamic ascent. As long as you are having warm enough above the convective threshold, then you can drive, except, of course, there is a exception. Over the Indian Ocean, actually, you can have subsidence. So during subsidence, you can cross the convective threshold but not have rain, because the warming is because there is subsidence, clear air, and there is a lot of sun. Right? So March, April, May, for example, you have very warm waters, but you don't have convection, because you largely are driving subsidence. So it's fairly simple. If you have no subsidence on top, or negative buoyancy as they call, and you have warm enough waters, you can drive dynamic ascent. That's what gives you a marine ITCZ. Okay? So we kept saying that El Nino does this, El Nino does that, but is El Nino just one thing? Is it always that you move the convection east and it rains over here, it gets dry over here, and so on and so forth? Of course not, because you have the zonal gradient in the mean conditions, which is driving the east-west circulation. But how far the convection moves during an El Nino really depends on many, many factors, including how much warm water has accumulated, who is pushing from this side, or who is reducing the push from this side. So remember, winds are pushing water that way, and you can have wind anomalies or weakened trade winds pushing this way or reducing this push. So that's what determines where the maximum warming happens during an El Nino. So you can do that using various techniques. This is one technique that's used in one of the papers. This is called one flavor of El Nino. Now the buzzword is ENSO diversity. Simpler word is ENSO flavors. So this is the second flavor, and this is the third flavor. You can see that they're slightly different. Why does it matter? Because the teleconnections, the word that we didn't use so far maybe, teleconnections basically means remotely driven anomalies. So if you have change in warming or cooling here, you are going to affect the monsoon. That is a teleconnection. Okay. You also change rainfall over Africa, over South America, and so on and so forth, North America, and so on and so forth. So where the maximum warming happens determines how the Walker cell is perturbed, how that affects the Hadley cell, and how the rainfall redistribution changes. So if this is 5 meters of rain per year, you know that that's a very massive heat source. That's what drives global circulation. So these are called extreme El Niños, where you have maximum warming along the South American coast, and the warming propagates because of waves all the way to Alaska and all the way to the southern tip of South America and so on. And this cluster 2 is got very little warming here and sometimes even colder temperatures. So the upwelling doesn't disappear, and the warming happens around the dateline. So if you remember that the convection in the normal conditions is around the dateline, that means this convection is just wobbling a little bit. It's not doing much here, but it's producing anomalies over here. So that is this, and it's called Central Pacific El Nino. This is called Extreme El Nino. This is called Central Pacific El Nino. And this is a more what is called canonical El Nino, or a cold tongue El Nino, because that happens over the entire cold tongue of temperatures that we have. And the question now that is being debated is whether, because of global warming, this flavor of El Nino is occurring more and more. It just so happens that since 1998, which was this flavor of extreme El Nino, these occurred more, and it almost occurred every 2 years. These tend to occur once in every 15 or 14, 15 years. These can occur every 2 to 7 years, whereas this seems to be occurring every 2 years. But this is a very short period, because 2015 was again this kind of an El Nino. So we are now back to having an extreme El Nino, which means what you have to remember is that there are flavors of El Nino that determines where the that is determined by where the maximum warming happens. And so it is the strength, frequency, and the flavor of El Nino that can change. That determines.
3.4 box.
3.4 basically goes from 90 west to 150 west. So it's basically 3.4 goes from 120 west to 150 west. So it's here. Nino 3 is 150 west to 90 west, which is more to the east. And Nino 4 is over here. Okay. So Nino 3.4 is combination of Nino 3 and 4. Okay. So on the other hand, La Nina has essentially one cluster. It doesn't differ very much, even though there's slight differences. Statistically, it's not very different. There are dynamical reasons why this happens, but we won't go into that. So that means it is well known that when the warming happens here, the atmospheric bridge works in such a way that the drought tends to be much more severe over the Indian Ocean. So the Central Pacific El Nino, or what is called also dateline El Nino, tends to produce a much stronger drought over the Indian region, which could be bad news if this is really becoming more frequent with global warming, because that would mean that you are having more severe droughts, and maybe more often, because this tends to happen more often with the short sample that we have. And there have been many droughts since 2000, 2002, I think, 4, 9, 12, 14, 15, many very severe droughts in the last 20 years. But you have to again put that in the context of what we said here. Is this a cycle? If so, is it going to go back? Right? Is this because of global warming, or is it just a cycle? This is a big question that we have to understand either from fundamental physics or from having long enough observations. The other thing that probably good mathematician or statistician can do that nobody has done surprisingly is, if monsoon is a very nonlinear system, it can have obviously lots of internal variability, right? It can just do something randomly. It doesn't need these large-scale constraints. It needs large-scale constraints of ITCZ and so on, but within that, it can have all kinds of variabilities. So if the start of the monsoon, as we said, is there's equatorial crossing of the ITCZ, then it splits, and then it goes north, produces two convergence zones, then can the first event be completely random? If it is, then can it then distribute the rest of the season based on randomly what happened here? So it's somewhat like saying the onset is quite random. Early onset tends to lead to wetter, more than normal rainfall, whereas a delayed onset typically doesn't give you excess rainfall. So is it possible that this is completely random? So you have 100 and whatever number of years of data. We have more than 100 years of data. Can we take that and make some kind of a calculation to show the relation between the probability distribution of the first event versus the events throughout the season? This is a good problem that somebody can work on. What else is happening? So we said monsoon is part of this global ITCZ, and we looked at animations of ITCZ, and we said it's going all the way across from the Atlantic into Indian and Pacific Oceans. And monsoon is splitting the ITCZ over the Indian Ocean, which means it should also affect the ITCZ in the other oceans. It can also mean that ITCZ can transmit signals from the other ocean as well, not just El Nino, right? So it turns out that actually that's exactly what happens. So this is the El Nino of the Atlantic Ocean. And the El Nino of the Atlantic Ocean happens in June, July, August, which is the same as the Indian monsoon season. And we said, I think we said before, because the Indian Ocean and the Pacific Ocean, the Atlantic Ocean are much smaller in zonal extent, the El Ninos cannot last as long. The El Nino in the Pacific lasts for 9 to 12 months because the waves, there are westward going waves in the ocean and atmosphere, and there are eastward going waves. Eastward going waves travel faster. It takes them 3 months to cross the Pacific, whereas the westward going waves travel much slower because of all this planetary rotation kind of things. And it takes them 9 months in the lower latitudes. That speed decreases greatly as you go to higher latitudes because it's dependent on Coriolis effect. Okay? And you can imagine that maybe I won't go into those kind of details. We didn't talk about them. So this extent is more than 15,000 kilometers. So obviously the waves and the communication of perturbations from here to here or here to there takes 9 to 12 months. So the El Nino cycle the life cycle of El Nino in the Pacific is 9 to 12 months long. Whereas these other oceans, Indian and Atlantic Ocean, are very small. So that only takes about 3 months. So in the Indian Ocean also there is an El Nino-like variability that we'll see in a minute. So the zonal extent in the deep tropics decides how long this zonal mode can last. Okay? So Atlantic also has trade winds, southeast, northeast, upwelling here, warm waters here. So it also has accumulation of warm water, discharge of warm water, droughts here, and so on and so forth. But it turns out that when this happens, the ITCZ is affected in such a way that the Indian Ocean, the Indian monsoon also gets affected. So this is showing the difference in rainfall between a cold or a La Nina in the Atlantic and the El Nino in the Atlantic. And you can see that the Western Ghats get more rain when it's colder here, and the core monsoon zone also gets more rain when it's cold here compared to when it's warm here. And it turns out that this process occurs through waves, again, because this disturbs the convection and the ITCZ. and hence you set off waves again. There are westward propagating waves, eastward propagating waves, which affect the depressions forming in the Bay of Bengal and so on and so forth. So there is another new paper now this year by this scientist student at INCOIS, and he explains how these things work. So it means if you think about the global map, then India is sitting here, the Pacific is here or on this side of the Indian Ocean. So the monsoon is getting hit both from the Atlantic side and from the Pacific side, right? So the other thing to remember is that this is peaking in June, July, August, whereas El Nino is peaking in December, January, February, and the monsoon is peaking in June, July, August, okay? What is happening in the Indian Ocean? It turns out that Indian Ocean also has a little east-west mode, zonal mode. The name Dipole has been debated for a long time, and there is some evidence that the Atlantic El Nino and the Indian Ocean El Nino happen independent of the Pacific El Nino, but there is some evidence that it's the Pacific El Nino that affects both the Atlantic and Indian Oceans. This debate is kind of dynamically complex. We won't go into that. But nonetheless, this El Nino is also argued to affect the monsoon, but that relation is not that strong, so you don't find very good papers on that. But what, if you want to explore, also you can think about is the El Nino is the big boss. It's very strong, a lot of heat source moving around, so that peaks in December, January, February. Monsoon is peaking in June, July, August. Atlantic El Nino is also peaking in June, July, August. And the Indian Ocean El Nino is peaking in September, October, November. Okay, we don't have very solid first principle hypotheses about why these seasons are phase locked to these particular parts of the year. There is arguments about the annual cycle and low order chaos. This all kinds of fancy works exist, but those are basically consistency checks. If El Nino happens in December, January, February, I can explain it this way. Doesn't say why it is in DJF, but okay, so it's kind of a consistency check. So you can think that this is the big boss and this is another big boss because monsoon is related to the land-ocean contrast and so on and so forth. So maybe these chota guys are only left with other ideas. So this one also took up September, October, November, so Atlantic has no choice. But these seasonalities of these tropical modes is not very well understood. So if you can explain that, then you can get some award, I'm sure. I don't know which one. Okay. What is the other complication? So we don't know exactly what is controlling the interannual variability of the monsoon and whether this control is coming through.
Pacific, Atlantic, Indian,
There are only 3 El Nino.
So why are we given 4 months? Sorry.
Monsoon, right? So you have El Nino, monsoon, Atlantic El Nino, and Indian Ocean El Nino. So essentially, we have all India monsoon rainfall, which would be nice to understand. It has interannual variability and intraseasonal variability. And we are saying interannual variability is affected by Eurasian snow, North Atlantic, North Pacific, Equatorial Atlantic, El Nino, so on and so forth. There is something even much more complicated, and that is that the distribution of rainfall over India looks really scary. If you are a forecaster and people are expecting you to forecast rain right there at the corner of, I don't know, Karnataka and what is this, Telangana or something, then you better have very good idea of whether your model has that kind of skill or not. So these are like, this 2016 was a normal year, which means all India rainfall was less than plus minus 10% variation. And this is, I think, 2017, I cannot read, 18, this was also a normal year. This was a drought year. 2013 was a normal excess year. 14, 15 were back-to-back droughts. So you can see that you just by looking at the distribution, you can hardly say which is normal year and which is drought year, right? So even though we are saying all India monsoon rainfall varies only within plus minus 10%, this is bad news because Marathwada can have plus minus 50%, North Karnataka can have plus minus 50%, Rajasthan gets only 200 millimeters of rain, but that can also be plus minus 60% or something, right? Coastal regions, obviously, if these regions are getting 2.5 meters of rain, even if they are minus 30%, that is still a lot of rain, right? Whereas here, if you're getting 500 to 700 millimeter of rain and you get 50% drought, then you are finished, right? So what remains largely ununderstood is what determines this rainfall. So you can go back to the concept of the popcorn kettle we used. March, April, May comes, everything gets very warm. There are instabilities everywhere. A lot of humidity is coming from the ocean, so the coastal regions get much more humid than interior regions and so on. But wherever it's raining, you can imagine in the morning it begins to get very humid, afternoon it rains or whatever. So humidity in general is high during March, April, May, and then during the rainy season, air is coming down, so on and so forth, right? So this is like a popcorn kettle, and then there are lots of corn kernels inside, then popcorns are popping everywhere. This is the forced ascent, right? So air has to go above, so it's going to rain here anyways. And this is the forced ascent because Himalayas are sitting there, so air has to rise, so the monsoon trough goes and crashes into the Himalayan foothills and stays there. And all here you have various processes happening, and which process extracts the rain is not always very clear. Plus, we are also depleting the soil moisture a lot, so you're already obviously changing the dynamic, and you're also irrigating a lot. That's also going to change the dynamic a lot. Okay, so there is large-scale circulation happening, moisture is coming from both sides, instability is built up. So if you look at things like outgoing long-wave radiation, which has a minimum when there are very tall clouds, you will get large-scale minimum outgoing long-wave radiation. Some people try to use that as a proxy for rain, but it doesn't work because within that high clouds, rain is like popcorn. Okay, so that's what makes this problem so very difficult. That is just in the mean, and then you have to explain how this distribution may be changing with global warming, or if it is changing with global warming.
So some of the places seem very stable across all of these years of monsoon, especially Odisha.
Yeah, so what would you do if you are a scientist and you are shown 6 years? Would you look at 6 years and conclude something, or would you look at 100?
That is for some particular process.
Well, if you have to think it the other way. Let's say we are saying all India monsoon rainfall remains within plus minus 10%, right? If that's true, then if some places are having plus minus 50, then somebody must be very close to plus minus 0 to get plus minus 10, right? So you are averaging over high rainfalls, low rainfalls, high rainfalls, average rainfalls, and so on. So obviously some places will have, Cherrapunji is going to have 14 meters or 13 meters, right? Bombay is going to have 2500 millimeters or maybe 2000 millimeters and so on. So that's the way you would think about it. Where is the average coming from? Basically averaging over very different distributions, right?
So apart from this popcorn picture of where there's OLR and it's going to rain randomly, is there anything more consistent to say if it's this OLR, there's conditions under which it will not rain?
OLR in that sense.
The OLR is low, but it's not raining. Is
Right.
there some other factor which you can bring in?
Yeah, so people look at CAPE, the convective available potential energy, or you can.
Isn't that directly connected to OLR? Like if the OLR is low, can you have CAPE high.
Not necessarily. OLR is the cloud top temperature. If you have deep clouds, you're going to get low OLR. But rain is not that scale. OLR scale is huge, right? Unless you have daily, hourly data, which is got high pixels, in which case you can see gradients of OLR. If you just look at even daily average OLR, you're going to get ITCZ scales. So you don't have the convection scales in them at all. So it's a problem of also the scales of the deep clouds versus actual convection rain. Okay. Okay. So going back to global warming, then what would you expect the response to be? So the first thing everybody wants to look is to see if land warming corresponds to extreme events in rainfall. Okay, this is nice work by Vittal from IIT Bombay, who's now postdoc somewhere in the US. And he looked at all the grid points and correlated temperature warming with extreme events, 95th percentile rain or whatever. And he found that basically only about 26% of the grid boxes over all of India give you a significant correlation between local warming and local extreme rainfall. Okay, which basically means land is warming, popcorn kettle is warming, but to rain, to create extreme rain, obviously you need to bring moisture from somewhere. Moisture is not available on land, so you have to bring in moisture from somewhere. So where does the moisture come from? So this is very nice work by Emmy, Patak, whatever, from IIT Bombay. And he looks at the rainfall in millimeters per day during an active period. So you can see that there is rain over this region, there is rain over this region, and the core monsoon zone. And you can see that there is some kind of a relation between the peninsular India and central India and so on and so forth. There is a stronger relation between core monsoon and the northeast, all kinds of north-south and east-west patterns, which gives you some idea of OLR and rain, because there is an interaction between southwesterlies and westerlies and so on and so forth, okay? But not very well understood. So this is the break anomaly. And if you look carefully, there is a cyclonic circulation here and there is an anticyclonic circulation here. And you can also see again what we said before. It is raining over the ocean. It's not raining over the ocean. It's raining over here. So convergence and ascent, descent and no convergence. But when it's raining here, it's not raining there. So this is our local Hadley cell, right? So you have to then look for moisture sources. So he takes the Indo-Gangetic Plain or the Ganga Basin, Western Indian Ocean, Central Indian Ocean, Upper Indian Ocean, and so on. There are many ways to do it, and then he identifies major sources and sources of moisture. Okay, so this is for a normal year or a composite of many, many years, where during the active monsoon period, Ganga Basin is getting rain, but this place is not getting rain. So the moisture source for this is largely from here. So during the break period, all the re-evaporation that happens here supplies large part of the rain here. Okay, so somebody was asking before about evaporation after rain. There is evaporation, but that is after you have had a long enough spell of active rainfall. Or this is also obviously a combination of irrigation, because there is massive irrigation on this in this bread basket of India, right? And this is the Western Indian Ocean. During active anomaly, Western Indian Ocean is supplying all these regions, which is basically this region. And moisture is not, this place is basically also supplying this region, so it's losing. And this is the break anomaly. So during the break anomaly, actually the rain is only over here, so you are only supplying moisture to this region, and so on. So there are large-scale moisture sources. Main thing to remember is that the land re-evaporation over the Ganga Basin is actually a significant contributor to the rain over the northeast. So there is this north. So during active period, raining here, not raining here. Break period, raining, not raining here, and raining here. Okay, that's something to remember. So we talked about the trends in extreme rain plus widespread floods. So if you look at the floods this year, it's basically over this whole region. I will show another map of the spread of the floods itself. So the paper by Roxy Matthew Cole from Indian Institute of Tropical Meteorology basically said that over the last 60 years, there is extreme rain, but the of widespread that cover more than 10,000 square kilometers has increased threefold. It used to be about 2 events, 6 per year. And for that, again, we tried to figure out what the moisture sources are. And you can see that. Sorry?
This is from the paper from IIT.
Yeah, so is Bangladesh part of India? No, Bangladesh should be somewhere here, right? But if I mean, this kind of sensitivity is everywhere, because in one meeting I showed a map which didn't show this as part of India, and somebody started shouting. So I'm surprised it happens in ICTS also. But basically, all the data we have is from India. But we don't have Bangladesh data, and Bangladesh didn't collect that much rain data. So we always try to, we would like to know what is happening to our friendly neighbors as well, right? But so Arabian Sea, which is warming, as I said, about 40 to 50% faster than the rest of the world, ocean, is supplying most of the moisture for the widespread floods. So the widespread floods happen essentially across this whole swath from the northwest to the southeast, including this region. All that excess moisture is mostly coming from the Arabian Sea. Bay of Bengal obviously is supplying some of it, and Central Indian Ocean, but you can see that this is more than these two together. And Central India re-evaporation itself is contributing about 29-30%. So this is kind of bad news, because if you are having widespread extremes and you are trying to reforest, adaptation, mitigation, everything, and if this ocean is warming and that's what is pumping moisture, and there is additional things happening here, there is a very significant negative trend in rainfall here. This land is warming very fast. They have had several years of more than 50-degree heat wave in the pre-monsoon months, which is a killer, right? Whether you are Taliban or whatever, you are not going to survive this kind of heat. So what happens here, if you're warming this, but this is much faster, right? So low pressure, high pressure, winds this way, so you are also getting a contribution. Coriolis will push you this way. So you are also, the temperature impact on pressure, global warming, is in fact pumping more moisture by adding winds, okay, to the southwesterly winds. So Arabian Sea warming, land ocean warming contrast together are pumping huge amount of moisture for this. So that relates to why this is not surprising. Land is warming, but unless you have moisture, you cannot create large-scale floods and extreme events. That is coming from warming of the ocean around. So even whatever you do here, if you cannot control this warming or this warming, you are going to get higher probability of extreme rain and widespread floods, right? What you can do is then forests obviously act as good dampers of excessive runoff and so on. So you can still do a lot. Even when you build cities, you can build with all these sustainable materials, permeable pavers, rain gardens, good drainage system, etc., etc. So you can still do a lot to deal with what will happen anyways. That's like managing the unavoidable, okay? So India is unique in that sense that we are trapped by the African highlands, Himalayan mountains, Burmese mountains, ocean that's warming and is getting a lot of warm water from the Southern Ocean. And what should be good news, that we are getting water, instead of being a desert at the same latitude, we are blessed with so much water, but we are managing to have lots of problems. Okay, so we talked originally about the onset, the withdrawal, and the length of the rainy season, and of course the propagation of northward monsoon intraseasonal oscillations. What is happening to those? This is study by Sahana from IIT Bombay as well, where she argued that if you look at the average onset date from 1950 to the present, there was a jump in the 1970s. Remember, we said there was also a climate regime shift in the 1970s, which we also invoked when we look at the, I don't know if I want to go back all the way, I'm almost. So this shift also we said is around the same time. So here, there is also a shift in the onset. So the onsets have become systematically later by a few days. Okay, so they used to happen earlier than the long-term average. So if this is like June 1, they would happen in the last week of May, but now they are happening more in the first, second week of June. The tough question here is, if global warming also picked up here, why should there be a shift? Did the shift happen and then global warming happened? Which would be the case if you're thinking of El Nino, for example. During that shift, there was also a shift in the El Ninos. Okay, there are more La Ninas in this period, weaker El Ninos. You had more El Ninos and stronger El Ninos and fewer La Ninas in this period. And does that look like a shift? Yes, because El Nino would redistribute the heat and that would make like a shift. Except that after 1998, we shifted back. But the monsoon onset, El Nino shifted back, but the monsoon onset didn't shift back. Okay, so does that mean that the natural variability is being modulated by global warming, or is something else happening? That is very difficult to figure out, but we will have to figure it out. Okay, what is happening to the withdrawal? So this is work by Sabir Ali from Indian Institute of Tropical Meteorology, who showed that around the same time, there has been a shift to earlier withdrawal of the monsoon. So you used to have withdrawal in, I think, in the third week of September, but after the 1970s, the monsoon started withdrawing earlier in maybe the second week of September. So now you can put your great mathematical skill to action and say if onset is happening earlier and withdrawal is happening later, withdrawal is happening earlier, what would happen to the length of the rainy season? Very good. Finally, 1 + 1 worked. Right? So here it is, the length of the rainy season is become shorter by a few days. Right? So you have to now combine the fact that mean monsoon decreased by, let's say, 10%, and length of the rainy season got squeezed by a little bit, and you have to then say, if the reduced rain is falling in fewer days, which would explain partly the extremes, right? If you change the number of rainy days and the amount of rain is reduced, but not as much as the length of the rainy season, then that can partly explain why extremes have increased, right? So in a very first order sense, that makes good sense.
Question about this. The shift that you have shown.
Yeah.
So that's roughly 1 or 2 days.
1 or 2
days.
I think the total is like 6 days there. Yeah. From there to there, yeah.
It may be 2 days.
It may be, yeah. It's more than 2 days, but this graph definitely doesn't give you that sense.
Yeah, maybe. Yeah. But that seems to be well within the.
Yeah. So this is.
Deviation. So what is the statistical significance of? I mean, how was this?
Yeah. So you know that people like Subimal Ghosh are kings of statistics. So they look also at PDFs. Maybe PDFs works better. But in the paper, they show that this is a statistically significant shift in the PDF and the onset date. So every talk I show this, people always come to that. But in the paper, which is just 4 or 5 pages, so you can read it easily, and there is supplemental material, they show this also is shown to be statistically, all of these are shown to be statistically significant by the people, and I'm not a statistician, but these people are, so you can definitely argue with them.
The onset thing is, just looking at it, it's not clear whether it's a shift or a trend.
Well, it depends on how you draw the line, right?
Yeah, so I can see like a upward thing, which looks even more scary.
As I said, statistics is that you torture the data sufficiently and it'll confess to anything. So they did it this way, and we are essentially arguing both sides, right? In the rainfall, we are showing similar one and saying that's a trend, whereas we are showing a similar one and saying it's a shift. But the shift tests are different than the trend tests. Okay, so they do this, I don't know, I'm not an expert in this, but so this, Sabir Ali had also drawn a trend line here, as you can see. In both of them, he has a trend line as well. But one thing that you do see in terms of shift is, going back to the land versus ocean, you can see that this is raining less over the ocean. Here, this is raining more over the ocean. So the shift in onset has come with this redistribution of land rain versus ocean rain. But one thing to remember there is that the ocean rain is not as reliable as land rain. So this problem is a bit of a difficult situation. This is the other paper also by Sabir Ali, separate one, where he looked at the propagation speed of the MISOs or the monsoon intraseasonal oscillations. And this is just showing lead lag versus the marine ITCZ to the monsoon trough. And the original propagation speed is in this solid line. With the warming since the 1979-80 period, the propagation speed has decreased. Northward propagation speed has decreased. In my mind, this is somewhat similar, that there are now studies arguing that cyclones and hurricanes are moving slower. It's not very well explained. Intuitively, first order, I would think if all these cyclonic systems are getting their energy from the ocean, because they have to take evaporation, condensation energy from the ocean. And if the ocean is getting warm, right, it's getting deeper, then amount of warm water you chew is now much more, right? So hurricanes, if you see, they are spinning, they upwell and they create cold patch, and then they move to warmer patch. So behind the hurricane, you constantly see this cold patch. Similar things happen here. So maybe the warming of the upper ocean explains the slower movement of cyclonic systems, but that is just kind of an intuitive explanation.
Are you saying that more massive objects are moving slower than also?
Not more massive object, it's the energy, right? These cyclonic systems, to sustain themselves, they need energy. Energy is coming from evaporation of the warm water, right?
They are also carrying moisture with them, and if they are carrying a lot of moisture, it will probably...
No, moisture. When you add moisture to air, does it get heavier or lighter?
Lighter.
Right? So you have to be careful, right? So that's not the explanation. The explanation is that why do they move? There is some relation to the energy available, right? So if there is more energy available, maybe they don't move on so fast. But this is very intuitive kind of explanation I'm giving you. Nonetheless, we have said a few things now. We said monsoon has the length of the rainy season. Extremes are increasing, widespread floods are increasing. Onset is maybe delayed. Not everybody is convinced, obviously. Withdrawal may be earlier. Not everybody is convinced. But these are moving slower, which Amit didn't complain about. Are you convinced about this one? So if monsoon is a system that, if monsoon is a system that is made up of the onset, withdrawal, and intraseasonal oscillations, then you are saying extremes are increasing, mean is decreasing. But nobody has looked at the consistency of all these things. Okay, later onset would probably tell you that that should decrease the monsoon, because later onset usually leads to a deficit or at least not excess rainfall. Earlier withdrawal obviously means shorter rainy season. This one we are not sure. So if you have a persistent pattern and a propagating pattern, we don't know the distribution of the amount of rainfall brought by these versus the standing trough that is dumping rain. Okay. On top of that, there is massive land use change going on. I don't know if you can see this clearly or not, but this is the satellite land use map from 1985 to 95. Here are the various categories of land cover, forest, others, cropland, shrubland, grassland, fallow land, and so on and so forth. And this is the change from this period to this period where there has been forest gain. I think Rama was asking this. There may be some places where there is forest gain. You have to look very hard. There is conversion of fallow and wastelands to croplands in many places, going from there to there. There is forest loss, which happens on a lot of places. I'm assuming black dots somewhere here. And crops to fallow lands, in other words, abandoned agricultural lands, and so on and so forth. So there has been large scale, this also shows you a scale of change of various land use. So obviously there is large scale land use change that is continuously happening, especially if you go around big metros like Chennai, Bangalore, Mumbai, Delhi. They are converting agricultural land into urban pavements, which obviously will make a difference in terms of the energy exchange between the atmosphere and land and the amount of moisture. For example, even moving thunderstorms, when they hit urban areas, because of soil moisture not being there, they split and they go around the cities. So there are all kind of local dynamics that happens.
So it helps the cities to not have soil moisture.
Well, not getting rain is help, then yeah, sure, why not? But also comes with urban heat islands. So if you are raining less, if you rain, evaporative cooling happens. If you are raining less and you have urban heat island, then is it helping? Maybe. Which city are you from? Thane, yeah. Thane is beyond help, but nonetheless. So again, using models, you can do these sorts of experiments. This was work by Supanta Paul from IIT Bombay, who is now faculty somewhere in Tripura or something. This is the land use or vegetation types you can get from MODIS satellites. So evergreens, needle leaf, broadleaf, and so on. So very detailed. This was a 10-kilometer grid. Doesn't look like 10 kilometers, does it? It looks pretty huge. That looks like a big, that may be global model. But anyway, so I was in Munnar 3 years ago during a break period, and I saw that over the vegetation you have this massive amount of moisture compared to the land areas. So I told him, I bet these vegetation here, all this green stuff, is acting like a capacitor. So during an active period, it is probably soaking up a lot of the moisture, and during the break period, it is giving up all the moisture. So he took the model and he removed this vegetation and showed that about 30-40% of the moisture supply for many regions here, especially Tamil Nadu, actually comes from the moisture from the Western Ghats. So they do have large scale impacts, but that paper also, it obviously is published, but Madhav Gadgil said, this is great, you should have written in Nature or Science, and somebody like Amit said, what crap is this? So people always have to be skeptical about science. That's what drives science. Only thing is you have to differentiate between skepticism and cynicism, right? Cynicism is like, skepticism is, how can this be explained to me, right? Skepticism is a good thing. Cynicism is what happens when you get old like me, right? So what is the good news in all this? India has invested, I don't know, several hundred, I think more than 500 crores since 2009 in starting dynamic monsoon forecasting, also improving weather forecasting. And I'm not showing monsoon forecasts here because they're having up and down years. They started in 2013. They had a couple of successes, couple of misses. And this year, everybody is watching closely. And today in Indian Express, the Secretary of MOES has written a long article on explaining what they are doing. But as I said, even if you do all India monsoon rainfall forecast, doing the distributions is almost impossible. Nonetheless, IMD has a statistical forecasting for district level rainfall forecast. So if you looked at the forecast they made on 10th July for 11, 12, 13, 14, heavy rainfall and floods were forecasted for all these regions. And few days later, is there a date here? On 13th, I think, Nepal did get massive floods. So the flood forecast was very good. So the 1 to 3 day forecasts and even 3 to 5 day forecasts have become very reliable from IMD. I think everybody has an idea of what these terminologies are. The forecasts are split into short range, which goes from day 1 to 3, medium range, which goes from day 3 to 10, and then what is called extended range, which is basically also called sub-seasonal, which goes week 2 to week 4. Okay, so this is the active break periods, Madden-Julian oscillation, and so on. These are basically weather, right? So beyond that, you obviously have seasonal to interannual forecasts, which 3 to 12 months or longer, right? So the thing to remember there is that everybody probably has heard that weather forecasting is chaotic. Weather gets chaotic after a few days because I think we saw before, very small differences in initial conditions can give you very different trajectories of where the weather will go in the next 2 to 3 days. So if weather forecasting gets chaotic in 3 to 5 days, how come we can make these kind of forecasts? That's the question, right? So this is called an initial value problem because you initialize the model with sea surface temperatures, humidity, winds, air temperature, and so on, and then you integrate, right? You assimilate models, in other words, data. In other words, you take data from satellites, from weather stations, from ocean buoys, ships, and so on. You tell the model, okay, here you are, integrate forward. This is much easier for mid-latitudes where the systems are large, they are 1,000-kilometer scale, and they last for 10 days. In the tropics, it's a nightmare because rain can organize in 1 or 2 hours very quickly. So tropical weather forecasting is very challenging, but still there are some skills, especially because of orographic rain, and so Bombay floods are forecasted quite accurately these days, and so on and so forth. So you look for where the skill of forecast comes from, right? So that's called initial value problem, whereas longer time scales, there is something else called predictability of the second kind. Okay, in the weather model, the ocean is just sitting quietly. You're giving it sea surface temperatures and you say it will remain same for the next few days. Whereas when you do extended range or seasonal forecasts, you have to tell it that ocean is also evolving. So you have to integrate the ocean and the atmosphere together. Okay, ocean has to evolve, atmosphere has to evolve, and that is called a boundary value problem because the ocean is the boundary that is giving all the energy from sea surface temperatures and so on and so forth. So the skill in weather forecasting is there, and there is some skill for extended range. Obviously, farmers want extended range because they want to know whether it's going to rain in the next few days or not, whether they should irrigate or not, and so on and so forth. And of course, seasonal forecast is also in high demand. So I kind of touched these and said, these will go on. They will worry about how climate change is affecting things, but when you do 3-day forecasts, you just hope that the climate change information has already gone in there. When you do extended range, same thing happens. Seasonal forecast, same thing happens. But there is also a Earth system model that is being run at IIT, Indian Institute of Tropical Meteorology in Pune, which is doing the so-called climate projections or AR6. So when they do AR6, so here you are fixing the ocean, you are fixing the aerosols, you are fixing land, everything. Here you are allowing the ocean to evolve. Sometimes you also allow aerosols to change and so on. Whereas here, you not only have to worry about ocean and aerosol, but you also have to worry about carbon, ocean ecosystems, vegetation, everything. So India, for the first time, is producing a climate assessment, climate projection, which is exciting. So they are hiring, I think, people. So if you're interested, you can join these teams. So India does, I think I've written an article on each of the agencies that does this. This is done in the National Center for Medium Range Weather Forecasting, which is in Noida. The boundary value stuff is done by Indian Institute of Tropical Meteorology, but they develop it and then they hand it to IMD. So IMD runs it and IMD makes the forecasts. And this is being done by so-called CCCR, which is Center for Climate Change Research, which is within IITM as well. Okay, so it's a good time for India in that sense that for the first time we have recognized the value of doing dynamic forecasting, dynamic modeling, monsoon research, which was all statistical before. Okay, now it's all dynamic. So let's conclude then. We didn't define technically what vulnerability is, but I think you have some sense. But there are metrics which measure agricultural vulnerability, infrastructure vulnerability, health vulnerability, and so on. And these regions means India, which feels very strong because of its economic development, is actually also highly vulnerable, but especially neighbors, Nepal, Bangladesh, Pakistan are also highly vulnerable. Sri Lanka may be better, but we don't know. Non-local factors complicate. So if Arabian Sea is warming and affecting your extreme events and widespread floods, then obviously you have to keep that in mind when you do your adaptation and mitigation within the country, right? Obviously you would probably want to do this for neighbors as well. And all these forecasts now are being given to all the neighbors, Nepal, Bangladesh, Pakistan, Sri Lanka, even African countries, I don't know who else. Every year, IITM holds workshops to train neighboring countries to use the forecast. So that is good news. So improving predictions, projections is an imperative. So hopefully this funding will continue. As you know, in India, all the smart kids want to join the finance industry or IT. After this summer work school is over, you are all going to apply for Infosys or something, right? So investment in weather, climate predictions and projections are paying off. So for example, we are developing early warning systems for health like typhoid, cholera, and so on, air quality, asthma, and fisheries. There are systems being developed for making predictions for crop conditions for farmers, which can help with insurance, crop insurance, and so on. So applications of these products, you can actually start small companies which will take these, build apps and give people how to track weather-related things. In India, we are not that fine-tuned, but in rich countries, people look at weather forecast for weekend plans, for beach plans, for ski plans, for travel, etc., etc. So it will happen soon enough as you all make more and more money. So there is money to be made here. I think we'll stop there and conclude the course. And I think they are all giving you some certificate with a check for. Are there any questions? I don't think we'll have question period today. So if you have questions, I left 15 minutes. We can have questions now.